Okay, record. Hello, everyone. And then share everything. Great. And then the PowerPoint. Cool. Did I miss anything? You've got the code, the my attendance code? No? Let's show that one. Hello. Excellent. That's the one. Yeah, this looks like it. BDXRIT. I'll put it here. BDXRIT. Okay. Started like the lighting again. Bit of this. Let's see if I can get the board on the. Now it stopped the mirroring. Let's try that. Okay. Good. And then the board somewhere there in the background. Seemingly, well, not very visible, is it? Okay, in any case, how are you guys doing? Yeah, great. You feel relaxed. No pressure. Okay. So I heard you had a lovely session with Phil last time. Was that the case?
Oh, I watched it online.
Huh?
I watched it online.
Oh, you watched it online. All right. Yeah, Phil said he was quite happy to watch along and all the rest. Are there any questions from that session? He told me that you kind of started discussing things and getting confused, and it was all lovely. You see, getting confused is quite crucial because it's like getting into the Severn tunnel and getting out of it as well. So we've been discussing waves. I think the first thing that kind of left over, I had some tasks at the end, and one of them was to research the term correlation, obviously in this technical sense. Did anyone manage? What can we say about correlation so far? Or at least could anyone introduce us to how we came to the term correlation? When was this crucial? What were we discussing when the term correlation became significant?
When two sources of sound are added?
Yes. Okay, namely? Let's get it rolling. So what was the case? When we added two sound sources, there was something going on when the sound sources were correlated and something slightly different when they were uncorrelated. What was that?
If they are correlated, they add 3 dBs of
Yes.
volume.
Yeah. And if they're not? Less. The thing is that the calculations we have actually have to do with fully correlated sound sources and fully decorrelated sound sources. So those are the two extremes. Actually, the correlation itself, it says here between -1 and +1, while actually in this context, we typically deal with correlation between 0 and 1. So 0 is no correlation and 1 is full correlation. Okay, so if you have correlated sound sources, then what you expect is interference, destructive or constructive interference. And when we have this type of interference, well, what happens is that essentially the sources add up, the waves add up. So it's one of my funny riddles, anecdotes. In acoustics, in signal processing, 1 + 1 is 1. Obviously, you expected it. I'm going to throw it off. Why am I saying this? Well, if you add two sine waves, right? How many sine waves do you get? I mean, two sine waves of the same frequency? You get one sine wave. Okay, so it's a slightly different way of thinking, of approaching this domain, from the apples in the basket, right? Because if you have two apples, you have, 1 plus 1 is always 2. But in the sense that the sound is not a material entity, right? The sound is the behavior of the medium. Okay, so just if you remember on Monday, I was saying, were all of you here on Monday? Just so I know, instrument recording acoustics, no. Instrument recording investigation, okay. So what I was saying then was that, so if you add up two sources which are the same, right? 1 plus 1 is essentially just another 1. And the reason is that the sound is not material, the sound is the behavior of the medium. So when you have transmission, right? When you have propagation of sound waves, what you actually have is that the molecules of the air don't really move across that much. They actually vibrate locally, right? So they essentially pass on the behavior. There is no material transmission in that sense, okay? So because of that, behavior is not additive like that. Apples are, but the behavior, the waves, aren't quite. Okay? Cool. So technically, we would have a -1 as an inverse correlation, but actually in the audio domain, what we have is that if we have a cyclic wave, right, then an inverse correlation, an inverse phase is actually full correlation with the time delay. Okay, so the correlation itself, what it allows us to do is first of all define, okay, two signals, how similar they are. That's pretty much it. But actually, once we get to cross correlation and autocorrelation measurements, then we get the ability to determine the time shift between signals. So how does this autocorrelation and cross correlation work? I'll just say a few things about this. It can be interesting. I mean, it kind of links into FFT as well. I guess you didn't do much FFT, yeah? Fourier analysis. It's slowly becoming part of this subject as we are developing it to become signals and acoustics, or acoustics and signals. I don't remember which we are on. So I will increasingly introduce some topics that are more related to signal processing. And one of these will be spectral analysis. This spectral analysis is a huge topic. You could actually make a whole module around it. And in a way, it links to autocorrelation as well. Okay, so if I have a signal, let's say it does this, and I have another signal, does this, then I can compute the cross correlation. Okay, so we have two terms. Cross correlation is the one that compares two different signals, and autocorrelation is the procedure whereby we essentially compare the signal to itself. Now, in this type of analysis, what we do is we produce time shifts. So we actually compute the similarity of these two signals, then we take the second signal and time shift it, and then compute it again, and then compute it again. So actually, the time, the autocorrelation and the cross-correlation function display the similarity across time. Okay, so this is my correlation and this is my time. So if I take these two signals, actually what I will get is some small amount of correlation until I have achieved this amount of time shift, when this peak starts to align with this one. So this amount of time shift, I'm getting some random stuff, and then suddenly I get something like a peak in my cross correlation function. Okay. So that's that's quite interesting because this procedure allows us to detect the time shift between signals. Okay, I mean, it's a brute force thing. There's nothing really clever about it. You say, well, I expect there to be a time shift between the two signals, or at least that after, with some time shift, the two signals will be more similar. And then you just do it brute force one by one, do all the shifts, compare the signal and so on. Okay, so that's one thing, that's your cross correlation, which can be useful. I mean, I don't quite expect you to, take two microphone signals and stick them into MATLAB and be able to, compute the cross correlation. But actually, if you're using some of these plugins that supposedly phase align microphone signals, then that's what's happening internally. Okay, they do this cross correlation and then they know what would be the time shift, which would make the signals very similar. So that's your cross correlation, and then the autocorrelation, what that does is it takes the exact same signal and shifts it in relation to itself. So with the autocorrelation function, you'll actually start at 1 for sure, because without the time shift, the signal is identical to itself. And then what you will have is that this will drop off fairly quickly. And then when I get to, again, this amount of time shift, okay, now it's a bit longer, because when this peak starts to align with this peak, about that time later, I will get a slight peak in this signal as well. So this is my autocorrelation function, again, versus time. So this is quite exciting because actually, this is coming close to telling us something about the spectrum of the sound. It's not exactly the spectral magnitude plot, which is the full term that covers the Fourier transform result. When you look at the spectrum, you look at the magnitude plot. I will probably take some half hours sometimes and get deeper into analysis. But it does tell me that there is a certain regularity here. Okay, and in fact, if this signal was to do this again, kind of be a periodic signal, then this would actually give me a sensation of pitch, to the extent that this time duration has anything to do with audible pitches. Okay, so obviously, it's not really part of the exam or anything, these correlation functions. But it's a useful thing to kind of have in your mind, okay, it's something along those lines. So when we say that we are dealing with uncorrelated signals or correlated signals, which are terms which will come up more frequently, that you have an idea of what it is. Okay, can you name two extremely correlated signals in this room? They are on, but there's nothing coming out of speakers. It could be, they could be very correlated. But actually, the signals that are currently in the room? Exactly. So as I'm speaking to you, right, there is a direct path. And there are reflected paths as well. So everything that is reflected of the walls is essentially also my voice. But it is rather correlated to the original signal. Okay. Now that you've mentioned speakers, it's quite exciting because that's where one of these interesting things come up, which is the double mono. I mean, actually, it's not part of the day, but who cares? What happens if I add up two signals with a time shift? So, exactly. What kind of filtering? Comb filtering. Very important. Okay. Do we know why? Yes, so the first important thing there is what is phase? Okay, so what is it actually? Huh? Well, not necessarily arriving, but indeed it has to do with time. It's a time difference. Phase difference is time difference. So what's the difference between a phase difference and a time difference? Why do we use the word phase to start with when it's just a delay? So what's the difference between delay and phase shift? Yeah, is it just a metric? So the crucial thing here is that phase difference is delay, which is frequency dependent. Okay, so what happens is that if I have a high frequency, let's say 1 kilohertz tone, and I have slightly lower 300 hertz tone, that should be about 3 of these per cycle. Okay, if I claim delay of 1 millisecond, okay, that's actually one period of the 1 kilohertz wave. Okay? That means that this wave is delayed this much, and it means that this one is delayed this much. If in turn I claim phase delay, phase difference of, let's say 2 pi or 360 degrees, then for this wave it is still 1 millisecond, but for this wave it's actually this much. It's 3 times more, a bit more than 3 times more. Okay, so if I talk about phase delay, phase difference, the duration of time that I'm talking about is relative to the frequency of the original signal, right? Because one full wave for a lower frequency evidently takes much longer time. Okay, cool. So if that is clear, then we can get to reasoning around why on earth do we get comb filtering when we add up delayed sound. Okay, does that suddenly go click?
Is muting some frequencies because it's not correlated.
They're all correlated. Yeah. All
but
the,
it's like inverse.
we have destructive interference. Okay. In this case, both waves are necessarily correlated, strong correlation. But what we're looking at, you see, we can look at the same values here, just to make it slightly simpler. So let's say I have a source. Does that look like a speaker? I don't know. Probably like this better, who knows? A source, a speaker, okay? I have a loudspeaker, I have a wall, and I have a receiver. Make this look like an ice cream. A microphone, okay? So I have a direct path, and I have the reflected path. So let's say that the difference, the delta here, the delta time is 1 millisecond. So it takes 1 millisecond longer for the reflected path to arrive to the receiver. Do we want to play the math? We should play a bit of math. What would be that difference in distance? 1 millisecond? So the speed of sound is 1 millimeter. No. The speed of sound is 340 meters per second. Okay. So what do I have? I have 1 millisecond. So what am I interested in? I'm interested in the meter. Okay. So if I travel 340 meters in 1 second, how many meters I travel in 1 millisecond, which is 1,000 of that? It is 0.34 meters. Okay? So that would have to be the path difference to get 1 millisecond delay. That's quite feasible. Yeah? Shall we do a bit of Pythagoras as well? Get the measures of the triangle? Get the brain rolling. I probably need a double coffee to get, to do this. Actually, what I normally do, I should start doing that again, is bring a huge pitcher of tea for these lectures. I will ask you to bring your cups, though. Unless you want to. So, shall we do the Pythagoras? We need 35 centimeters extra between these vertices. Warning. What do we know about this reflection here? It's not necessarily right angle. No, that's the problem. I would hope for the right angle. So these are identical angles, which means that this is an isosceles. Flat triangle. Sorry, I've never studied math in English. But we know that these are right angles. Right, these are. Could have a play with it. Never mind. Let's not. Okay, we'll never get to the first slide. It will take an hour. So that's feasible. So let's go back to reasoning around what happens to the spectrum when we add the same sound to itself with a 1 millisecond delay. So we know everything about constructive and destructive interference, yes? So this means that if I have 1 millisecond, and I'm going to try to sketch the spectrum of this, and we're looking at the spectral response of that interference, then we have amplitude versus frequency. And I've already figured out that 1 kilohertz, if I delay it by 1 millisecond, it's a full cycle. So I will have a full constructive interference. So I will have a peak there, whatever that is. Essentially, I can do here something like double amplitude, or I should be doing dBs, 3 or 6 dBs. That's the eternal question. Wake you up in the middle. Is it 3 or 6? When you said 3, I was actually, oh no, is it 3 or 6? Well, maybe it's 6, maybe 3. Let's skip this. Well, actually, the doubling, it all depends whether you're doubling the level or you're doubling the pressure. We'll probably talk about this in a second. Anyhow, this is the peak. Let's get to this frequency, this spectral response here. So I have a peak there. Now the question is, where do I have a trough? Okay, so what I'm looking for is a frequency for which 1 millisecond is 180 degrees shift. Okay, that would be causing destructive interference. And I can actually figure it that if I take half this frequency, try to draw this more or less accurately, then this 1 millisecond delay will put the signal exactly out of phase. Okay, so at 500 hertz, what I get is full destructive interference. I mean, if these are actually fully correlated signal, there's nothing left there. If it's a reflection of the wall, there is something left because there are anomalies and all the rest. Okay, so if I keep lowering the frequency, do I get another point of full constructive interference? Shall we leave that question for later? Let's look at what happens slightly at higher frequencies. Okay, so what can I do? What can be funny if I keep pushing this frequency up? So I'm getting higher frequencies there. When is the next trough? Because obviously I'm expecting a trough here. So I have, again, this amount of time delay, and I'm pushing the frequency, okay? So actually what I need to get to is this point, right? So if this is my waveform, goes on, and I have this amount of delay, then I'm getting, again, fully out of phase. What is the frequency relationship between this and this? I think it's 1.5, right? So this would be 1, but actually it's squeezed in another half wave. So actually at 1.5 kilohertz, I get a trough. If I have a 2 kilohertz wave, then I've actually done 2 full runs in 1 millisecond, again, a peak, and so on. Okay, now, can we answer the question, what happens below 500 hertz? Is there another peak of constructive interference if I keep lowering this frequency?
Could be.
Yeah, where?
Actually.
I don't think so.
No.
No, huh? You imagine this, yeah, this is the duration, I'm kind of stretching it, it's filling it in more, filling it more, filling it more, filling it more. The next full correlation peak is actually 0. And what you get is a pattern whereby these troughs are actually linearly spaced. So this will be 1, this will be 2, 2.5, and so on. Okay, so that's how this comb filtering pattern arises in relation to adding a fully correlated sound to itself with a slight delay. Okay, so now comes this producer's dilemma. Do I put a mono sample in my stereo track? And if I do, how do I do it? What happens if I put a mono sample bang in the middle in my track? As you suggested, fully correlated sound coming out of the 2 speakers. When is that an issue? No. When do I expect comb filtering at the receiver?
If there is reflection.
No. Well, that's anyhow the case. But when is it more problematic in relation to the receiver?
High frequencies.
There has to be a path distance difference. Which means that if you're bang in the middle of the 2 speakers, there is no issue. But if you're slightly off, then you get comb filtering. Okay, so you can test this, you know, don't trust me. If you trust me, you're making me a priest and you're making this a religious gathering. There is no room for trust and belief in here, only skepsis, right? Distrust me as much as you can, verify everything I say. Right, so if I'm in the middle and I put a mono snare sample bang in the middle, lush, nice, central, everything, and then I move out of the middle, do I hear comb filtering? Try it. Okay. I mean, if I play out a sine wave, I'm not sure if we get more into signals, and probably we will. In every lecture, I will cheat in half an hour of signals. Then, and if I play the same sine wave out of 2 speakers and you move around the room, it's all over the place. You probably heard this, okay? So what's the solution there? Because in a club, how many people are standing bang in the middle of the, you know, throughout the gig? Well, I am, but there's very few of me in a club normally. So what do you do then in order to make this snare sound somewhat more reliably presented across the listening rooms? Have more speakers? Well, more delayed paths, more comb filters. Although the truth of the matter is, just a second, is that if you have many comp filters, which have different characteristic or different set of frequencies, then they eventually even out. So it's probably something that came from the experience of like, okay, in a club where you have two speakers, the sound is, you know, here and there. But if you have a lot of speakers, and that's actually also what they do in order to balance the levels out, right? Because if you have two huge speakers in a concert, you come close to them, you're blown away. But if you have a distributed set of speakers, then everywhere you can actually have a fairly reasonable level. And you've noticed probably also that the timbre, the quality of sound is better. So by all means. But let's say we're still in the studio. What was your idea?
No, there was a person waiting.
Oh, thank you. Okay, so what was, I mean, the answer may or may not mean much at this stage, but it's actually the term that we're discussing now. So if you have problem with correlated sound coming out of the two speakers, what do? It's what a 5-year-old will probably come up with, it's decorrelated, and that is the right answer. Okay, so decorrelation is a procedure in signal processing. So you might not have heard of it before, but it's actually one of the funkiest ones as well. So typically, I'm actually lucky to know the guy who has coded the decorrelation for Dolby Atmos. A great guy from New Zealand, Australia, New Zealand. Same. Only a few thousand miles away from each other. Aussies and Kiwis, one punch. And it's a tricky thing. So what does it mean to decorrelate the sound?
It's a completely different sound.
Yeah, but that's the problem. So I'm trying to have the same snare sound, but then it seems to be completely different. How on earth is that possible? What are we talking about? Huh?
The small delay.
Well, with a small delay, you get comp filtering. If you add up the sound to itself with smaller delay, that's just comp filtering back again. That's what we're trying to avoid, actually. So the crucial thing here is messing up the phase. Okay, so what you would get is a little bit of delay back and forth, but different for all frequencies. That would be your decorrelation, ideally. Okay, so messing up the phase spectrum of the sound. That's what you do. And then, well, how do you do this? Convolution, lovely term, that's it, yeah. You can convolve with noise. Okay, so we're gonna talk about convolution in more detail at some point. And I should probably write up new slides for these bits that I'm introducing at random. But you know, if there is a mystery around it, maybe it's more interesting. And if you have to look it up rather than it being available, that's also interesting. Can I take a huge tangent here? I was thinking of, the first thing I was thinking of buying, you know, 5 amazing mastering compressors and 5 amazing mastering EQs for us. That's one thing we're missing here, right? That kind of gear. And I was like, well, how do we do this? So I thought, well, actually, we can make a research around this that relates to the usage. So my hypothesis is that if we have a studio, a mastering studio here, and we have, you know, 5 mastering compressors, 5K each, and 5 mastering equalizers, 5K each, lovely sum of 50K just at your fingertips, yeah. But the trick would be the reason, you know, the way to buy this, I thought, because obviously they won't just buy it straight out, unfortunately. I would if it was up to me. But the idea was that if you have this mastering studio and you have these 10 things in the rack, and we measure the usage, right? So we have some kind of trick in the back of the devices that actually measures how much is each one used. And the idea is that if you have all of them, all the 10 of them available, they will be used much less compared to the situation where we would say, okay, for 2 weeks, we have only this EQ and only this compressor. Next 2 weeks, only this EQ and only this compressor, and actually have them exclusively available. And the thesis is that if you have them exclusively available, then you would actually get to use all of them. And if not, you probably won't. I mean, even the fact that it's a 5,000 pound thing in front of you and you're unlikely to ever buy one yourself, you know, it's still like, yeah, but, you know, after the third one, you're like, okay, this one is fine, right? Same thing with plugins. If you have millions of plugins, you never get to use them, right? So in that sense, this idea that availability is detrimental to motivation to explore is something that I think could be measured even, rather than just, you know, projected. So in that sense, you know, having everything available, everything is on the slides, you can always find it. It actually stops you from doing this, right? And if you come out of this lecture with some or other, you know, idea which is still slightly confusing, and you can't really find it in the slides either, it may actually start bothering you. And you might actually go out and find out. But if it's all there, like, well, I wasn't sure what it was, but anyway, I can look it up. You see? So actually, that's the kind of thing that my generation didn't suffer from, because stuff wasn't available like that. You know, you actually had to go places. For me to synthesize my first sine wave, it took a few years. You know, with the old 386 PC, whatever stupid grab a sound card back in the day, no real internet at that stage. It's like, I knew what a sine wave was. I had a sound card that could produce arbitrary waveforms. I knew some C++ as a kid, but to program a sine wave, it was like, you know, it's like impossible. And then when the first time I saw the code for a sine wave, that was it. You know, I was supposed to stay like that for the rest of my life. You know, because it's really important to have this burning question, something that you cannot find, something that is a challenge. Okay, so that's my justification of not having most of this in the slides. Okay, cool. So decorrelation, let's try to wrap this up here. So decorrelation is essentially messing up the phase of the sound. Yes?
So when you mix it down to mono,
yeah,
that like destroy your mix. Yeah.
The decorrelation.
Yeah, if you have multiple like phase issues.
Well, what destroys your mix in a mono mixdown, which is again becoming more popular with these Bluetooth speakers. There was about 10 years when no one was doing mono, but now it's back on track. The issue that you can get is if you use delayed-based panning. Okay, so panning is one of those funny things. Actually, if you're interested, I don't know if anyone still runs 32-bit audio unit plugins, but I have a thing called PsychoPan, which is a psychoacoustic, I probably mentioned it last year, psychoacoustic-based panner, where you have different ways of panning things left and right. And one of them is delay. And if you do that, it works lovely in the stereo, but if you mix it down to mono, then you get comp filtering, because you've actually mixed the same signal with itself, with the delayed version of itself. Okay. So actually with decorrelation, you don't have a mono mix problem. But the decorrelation I was mentioning, the Dolby Atmos, is the most crucial tool if you want to induce the sense of the size of a sound source. So I don't know if anyone's playing with the Atmos or had the chance. There is a dial which says size. So you have the location of the sound source, you can modulate that, but you also have the size. And we were lucky enough to sit in Dolby's whatever private theater. It's not too far away from Bristol.
It is one in Acoustics, but it's a big one, I think.
Ah, but that's just a cinema. This is like their research facility. So it's in the Dolby headquarters. They have a cinema, obviously, but it's not huge. Maybe twice this room.
One in London.
A Dolby
So
headquarters?
yeah,
Yeah? Or just a cinema with the Atmos?
they have multiple like suites essentially.
All right, yeah. So what we had a chance to sit there, and they had the size parameter, and I was like, okay, let's hear it. And they push the size, and it actually grows. But because I know the ins and outs of this, I'm like, okay, can you please put a really fast modulation on the size so that it grows, gets smaller, grows, gets smaller, grows. And actually it was anomaly free. And I was totally stunned, because that's the real tricky thing, to make it such that modulating this size parameter back and forth does not give you crap. Okay. So that's how it's done. You introduce the sense of larger sound source by playing it out of multiple adjacent speakers, but every speaker has to get a decorrelated version of the sound source. Okay, so one of these things, I mean, you can play with this convolution with noise, but where did you encounter the term convolution? Probably before? Reverb, yes. So actually, the way you can get a poor man's decorrelation is just get a really short delay time reverb, remove the pre-delay time, make it such that you don't hear the characteristic of the reverb, try to get as flat as possible in terms of the reverb characteristic, and that's your little decorrelation. Okay, so in effect, if you have a good reverb and you make it unnoticeable, and you put it on your mono sound, which is in the center, and it's a good reverb, it will do different things left and right, then you're sorted already. So try it. Yeah? Take your mono snare sound. The reason why I'm saying snare sound is because it's a broadband thing, so you're most likely to hear the comp filtering effects. Okay. Put your snare sound bang in the middle, move around the room. Now take the same snare sound, do a little bit of unnoticeable reverb on it, and then move around the room. Okay, and if you've done it well, you should notice much less comp filtering happening right there. Okay, that's great. Shall we get onto the first slide? Well, we're still not even in the zeros. We're still in the zero slides among those. There was a task last week about calculating correlation of signals. It's actually funny. You can also do a spectral analysis with like an 8-point signal, believe it or not. And that's probably the only way to fully understand what it does, but we'll get to that. And then we had these little questions, which were a bit more loose or easier potentially. So what we were thinking of is, can we create a channel, an acoustical channel based on refraction? Okay, so what was refraction? It was the bending of the waves due to medium properties. Okay, so if you go from hot to cold, from cold to hot, you will get bending. If you go from less dense to more dense, vice versa, you will get bending as well. Okay, so the waves bend. I mean, why is this a funny thing to say? The waves bend. Well, they're bent already, aren't they? Right. So it's again crucial to. I don't know if this was quite clear in the video from last week, but you see, if I have a wavefront, I can depict it like this, but I can also depict it like that. Okay. So I actually have a kind of a wave paradigm, and I have a particle paradigm, like a direction of movement. Okay. So when I say the wave is bending, what it means to say is that this arrow type thing is bending. And the question, so is the sound a wave or an arrow? What's the answer to that question? Huh? Well, both or neither. It doesn't really matter. Actually, I would say it's neither because these are concepts. And the sound is not a concept. It's actually something we perceive, something which is more evident and real. Okay, so waves will bend down when medium is warmer above. If you can imagine a situation that it's quite cold close to the earth and quite warm above. And waves are downstream the medium flow. So waves will bend down if warmer above and if downstream the wind. Okay, so this is this game whether we can come up with a situation with the temperature difference and the direction of the wind in relation to the wave in order to produce an acoustic channel. So what's interesting about acoustic channels is this. This is an acoustic channel as well. Okay, so when I get reflections from both sides, I get this channeling effect. So what happens then? More coffee. I actually perceive a louder sound, right? Because there is less of it escaping in other directions. It's more focused. All these paths actually crisscross and keep this direction. So I get to hear it louder. So acoustic channeling is quite important. Okay. Anyone studied underwater acoustic channeling? Go ahead if you feel like it's interesting. Okay. Combining SPL of uncorrelated sound sources. Did anyone get into that? Are we losing it? Shall we have a break shortly? Or coffee break? Tea pitcher break. I still have to figure out if the old pitcher is in the office. Anyone want to throw up the equation for adding up uncorrelated sound sources? Are we interested in this? I mean, you know, guys, the only thing you will ever learn are the things you're interested in. So if you're not, I'm not even pushing it.
I think that I remember.
Yeah?
At least I remember like the equation for dBs and SPLs, like 20 logarithmic.
Okay, let's start there. Okay, a bit of math before the break. Is that a good idea? You remember what was my task from the initial session? Yeah. To calculate the age difference in dB. Yeah. Did you manage that? Should we try to?
I know the equation. I didn't.
Let's try that. Okay. So my typical dilemma was finding a suitably young partner for me without being called weird names. Okay. So, and the idea was that if I'm 39 right now and my partner is 29, then that is all right. Yeah, thank you. But when I was 25 and my partner was 15, that wasn't as fine. Okay. So evidently, this in terms of the difference here. So the age difference in both cases in 10 is 10 years. So this means that the difference doesn't tell me much about the relationship of the age. And hopefully the dB scale will. And that's about it actually. So what do? Is I take this ratio and then I take the logarithm of it. So the equation was, right, we have two equations. One is the 10 log of the ratio, A over B, and the other one is the 20 log of ratio A over B. Okay, and the relationship here is that actually this is the same. I shouldn't be calling this A and B because it then relates to the same thing, but this is the same as 10 log of A squared over B squared. Okay, that's your little log manipulation if you remember the math. Whatever is in the exponent behind the log, you can take out as a multiplier in front of the log. Okay, so and that's that. If you kind of remember this taking out of the exponent, you know, it makes the log slightly more understandable. But it also shows you that in physics, if what you're looking at are pressure values, right? So typically, what's a good word here? Can't come up with it now. Let's say pressure, that's one of them at least. Then you use 20 log. But if you're using power, which is the square of the pressure, right? So as soon as you have something energy related, then you use the 10 log. If you like to remember this. So in any case, the age here is not power related. So I can use the 20 log. So I can do the little calculation here. Let's see if this works. So for me, my calculator is called Super Collider, which is a lovely thing to code audio anyway. If I can get that to talk to me. Okay, here we go. So what do we have? We have 39 over 29. Okay, that's 1.34. Okay, and then what I do is I take the log of that, and I think log 10 is the one for this. Okay, and then I do 20 times that. Okay, so actually that is 2.57 dB. Okay, and then I can also, I can verify this. So if I have a doubling of amplitude, it's 6 dB. Okay, if I have doubling of power, it's 3 dB. Okay, that's your little wake up call. That should be funny. Imagine having your you know, wake up tunes like random acoustic questions. Like first, oh, what is this? It's like, oh, what is that? Maybe I should do that to myself. I like to be masochistic to a certain degree. At about age 15, I've decided I'm not going to listen to 4/4 music ever again. And I've started systemically erasing everything in my collection that was in 4/4. And it lasted at least 5 years. And I still feel the benefits of this decision. Okay, so that was the dB difference.
So can we repeat the double in SPL is 6 dB?
Yes. Yeah. And then if this affair happened 14 years ago, and we were 25 and 15, then this is 4.4 dB, right? So from 2.6, let's say, to 4.4, you see that there is a difference. So now the question is, if I find, let's say that the relationship is safe before, you know, people frown on you. Obviously in private, most things are safe, but let's say 2.5 dB is the limit. Okay, if your partner is 2.5 dB older or younger than you are, then you're at the limit. So could we calculate at the age of 25 what would have been my limit? Right? So what I'm saying here is that this ratio has a dB value of 2.5 something. Let's round it up to 2.5. This one has, what was it, 4.4. So the question is, if I'm now 39, right, what would be the 2.5 dB younger partner for me? Because I figure out, okay, 2.5 is good. So to verify whether 2.5 is good, we have to see what would need to be the age of my partner when I'm 25, which is 2.5 dB less, in order for this to be feasible or not. How do we do that? So this is where things become slightly more complex or tricky. Shall we try to look up the equation? What is it? Log dB equations. Let's see how quick I am with this. Decibel dB formula. Typically with this stuff, it's good to look at the images because then you immediately see whether you have it back and forth. Okay, so I'm looking for the backwards thing here. Maybe it wasn't useful to look at the images here. Formula recall. This one looks good. P, no power output, you see, so with power it's 10, the multiplier is 10, that's good. We can also just look up the log formula and figure that out. SPL, it's also this direction. So what we need to do is figure it out the other way around. Okay, so what we're saying is that, let's say X is 20 log A over B. And the question is, what is B? So I'm looking to find out this age. I know X is 2.5 and AB. Shall we leave this for the break if you find it out? Let's see, because that's part of the game. You know, see if you can figure it out. Because you see, we're gonna have an open book exam anyway. So your ability to find things out is crucial here. But one thing before we break, which is something I want to show you. See, this is 4.4 dB difference. How much difference would this be? For a good answer, a cup of tea. I've just swapped around the two numbers. What do you expect to be the dB value? Huh? Excellent. Minus 4.4 dB. Cup of tea. Yeah? So you see how it actually really works well. You can have a ratio of two things and it tells you how much larger the other one is than the other. But if you invert this ratio, you actually get the negative of that same value.
But I have a question. So
Yes.
for sound, not for ages, for sound, that division is the current sound pressure divided by the reference.
By the reference.
Well, what is the reference? What that means?
Reference is just a reference. It's like a random thing.
Previous sound or
It's like a meter. What is a meter? It's in a museum in the Paris.
Ah, okay. So it's every time is the same.
It's every time the same. Yeah. I think it's calculated based on the threshold of hearing at 1 kilohertz, something like this. Okay. Cool. So let's have a generous 15-minute break and figure out that. So I'm bringing 2 cups of tea. One for the currently, was that you? Yeah, one for you for the -4, and the other one for whomever calculates what would be the B here. So instead of 50, if someone is 2.5 dB younger than someone who is 25, what is the age there? Okay, so that's the other cup of coffee. And then sorry, it could be coffee as well. Prefer coffee or tea?
Let's see.
Tea, all right. Well, I'll bring another tea, then I don't know who's going to be the winner. Maybe I'm going to have another 2 cups. If no one does. Okay? I'll see you in a minute.
So T is this the yeah. That's why it's not like
found the picture. So these are the kitchen desk. Are they stable enough for this? So yeah, I don't want to discriminate between people who provide the right answers and who don't. So grab a little cup. Beware, this is proper Turkish style black tea, which makes you go, whoa. And the next day when you don't have it, it makes you go, whoa. So, you know, the better the drug, the worse the withdrawal, as usual. But this is still in the legal domain, so I will be drinking it as well. We can give it a few minutes. Settle. Okay, so the question is, did anyone get to the bottom of this riddle? Is that a riddle at all? What can I remove here? Let's remove this. What is 2.5 dB less than 25? That was the question. Okay, this is actually a good bit here. These question marks are not very helpful. Yeah, so how do we get rid of the log? So probably you know bits about solving equations in terms of, you know, take it to one side, take it to the other side. Yeah, this is something that could work. But the problem is, what do I do with the log? Okay, so how do I get rid of it? So if I have a so let's say log 10 base log. Obviously here I didn't specify it because it's kind of self-explanatory. But if I have 10 log of A equals B, how do I solve this equation? It's a bit faint, is it?
Divide both sides by log.
No. What is antilog? The exponent. So if I take both sides to the power of 10, then A equals B to the power of 10. You see, if I take log 10 of A to the power of 10, I get A. So the log is defined as the inverse of exponentiation. Okay, so that's the little trick you need to remember, I guess, or look it up. And then this one, how will it look? Well, first of all, I have to get only the log to that side. So it's x over 20 equals log of A over B. Okay. And then I take both sides to the power of 10, which means that A over B, ooh, that doesn't look like an A. We're drooping A. A over B equals, sorry, A over B to the power of 10 equals x over 20. Okay. What do I do next? Well, this is actually the same as A to the power of 10 over B to the power of 10. So I can multiply, and I'm interested in B, right? So B to the power of 10, let's take one more step, equals A over this. So 2A to the power of 10 over x. Following? I hope I'm doing the right thing. And then B equals this 10th root, yeah, of 2A 10 over x. And I can take the A out of this, so B is, sorry, B is there already. So this is the same as, I hope I'm making sense. I didn't do this for a year at least. A times 2 over x. I have no clue what I've just done. Let's see if I can get it in code. Okay, so what I'm saying then is that, let's just try this final thing. You will excuse me if it's all wrong, but what it says is that B is A times, so A was 25 times the 10th root. Am I doing this right? Who knows? I'm not sure about the 10th root. That's a bit tricky there.
What I don't know is why x divided 20 elevated to 10 is x divided 2.
You can change it. You can change the T to.
Yeah,
That's
that's right.
Am I supposed to have a 20 here? Yeah.
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 Throughout.
Yeah.
Yeah. Let me hear you say yeah. Okay, well, I'm totally suspicious about this anyway, but let's try. So what I'm trying to say is 25, and then I have 20 over x, which is 20 over 2.5, and that to the power of 1 over 10. And that's 20. That makes sense. Okay, so what I'm saying is that if at the age of 39, I have a partner who's 29, that's fine. And the same relationship is obtained when I'm 25 and my partner is 20, which is also fine, right? Yeah. Just on the border. 25, 19, 25, 20, yay. Okay. Cool. So we're through with that. That's that. I mean, there will be similar things in the exam. You know, a bit of calculation didn't hurt anyone. Well, they probably did, but it depends on the context, I guess. Okay, so shall we get on with today's lecture then? Objects. Okay, so we've done a bit of funny things. I invite you to pour yourself a cup of brew. I will do that just to show you that it's not poison, right? I have to be the first. But this is strong stuff, guys. I mean, please be careful. And come on. Grab a cup. I have a limited amount of these disposable ones. So if you like this type of tea, I invite you to keep bringing your own to these classes. I mean, even if you're used to drinking with milk, you will see that this one actually works quite well out of the box. Short and yoo-hoo. Makes you gonna wanna go wild. Yeah. Were there sufficient cups? Yeah. Huh? Wow. Yeah. Excellent one. One left as well? Yeah. It's a bit hot for now, yeah. It's nice.
Where can you buy this?
They do something in Turkish shops, and they sell it only in like half kilo, you know.
Tray sizes.
Yeah. So what? No. Well, actually, supposedly it's a different. It's a different substance. That's what they taught me. It's tea.
Yeah.
But then again, it's a similar stimulant type of thing. I don't know. It does get you addicted in any case. Just you know. That's what you want. That's what you want. Addicted to acoustics, addicted to tea, and it's actually one of the ways I'm gonna have you addicted to this early session. You know.
Yeah.
Oh, you're awake. Well, I really don't want to go in, but there will be Turkish tea. Can you make it for 10? I mean, obviously I can't make it for 10. I was thinking like, yeah, let's push it a bit, 10:30, you know, play with this. But no, let's do it 10 o'clock. It's good to have all the time in the world. I mean, evidently today we'll go until 1, but if we start at normal time, we might as well start drumming earlier.
This is all recorded in that, isn't it?
Yes.
Because I'm finding a project meeting at 20 past 12. I'm gonna have to shoot off to. So
all right.
The rest, if that's all right. Just
Sure. Yeah. No worries. I mean, it's not a meeting with me, is it?
No.
Good.
I'll still today, but
Huh?
later on.
I got one.
At 1, you got one with me today?
Yeah.
Good. I should still be here. I'm feeling like, oh, my headache is kicking in.
Only a 15-minute session because on Tuesday I've seen the time slots are like.
Yeah, it's 15-minute time slots, and if you want a longer one, you book 2. And if there's no one after you, we can chat on. It's just that on paper, I have already 16 students, and there should be more with the master students as well. And typically, not many show up. But just to be on the safe side, I make these short slots, and then we're there until it lasts. And evidently, if you say like, well, actually, this week, if you skipped a few weeks, I really need 2 slots, just feel free to make a double booking. All right. Hello. A bit of shoulder exercise on the screen. Good. So here we come. Today's topic is objects. Okay, so we worked around the waves, around different things here, correlation of waves. All of these things are rather useful, I would think. So today we're going to talk about what an object, a physical presence of solid matter, does to waves. Okay, briefly about reflection, bits about standing waves, diffraction, scattering, resonance. Okay, so what is going on with the reflection? Well, the basic scenario here is, I can actually hide this or not. This makes it smaller. Yes. Okay. So what happens is that, as I said, these sound waves are actually the behavior of the medium, and that behavior propagates. Okay. So in this sense, we can depict this as these balls, which are essentially locally fairly static. They still are able to transmit the wave. Okay, so you can kind of imagine them coming closer together, then this one is pushed away, and then this one is pushed away, pushed away, pushed away. So eventually we come to the hard boundary. And at the hard boundary here, it's just reflected back and the wave goes back. Okay, so the thing here is that what happens is we call this phase inverting reflection. Okay, so that's a bit of a, well, I mean, I was kind of thinking about this. Does it actually really matter? And there is one situation where it does actually really matter if you get into physical modeling. Okay, so I don't know, you've probably had a bit of APDI. How many people done APDI? Yeah, so you know bits about physical modeling. And actually, when you have a waveguide, which is just a delay line, and you make a feedback on this delay line, you can already get a pitched sound coming out of it. Okay, but actually, if you're wanting to model a proper string, if it's not just a bare bones waveguide, then at the termination, at the hard termination of the string, you should actually put in a phase inversion times -1. Okay. So there are some situations where this is practically useful, but then again, we're extending our theoretical knowledge here. And if you have a hard boundary, you get a phase inverting reflection. You do get a non-phase inverting reflection if you don't. Okay, so what it is we have a dramatic impedance increase. And we are dealing again with the bits. So actually, I should go from the beginning here, if not everyone was on Monday's lecture. So what we're looking at is velocity waves and pressure waves. Although it was part of the lecture you've seen online last week, yeah. So velocity and pressure waves. What is the difference?
They are.
Yes, they're out of phase. Okay, so when one is at maximum, the other one is at minimum. And how does this work in the space around me? So if I have a hard wall, do I have a pressure buildup or do I have a velocity buildup against the wall? Pressure buildup. Okay, so you can also remember this if you know that if you're in a club and you go straight against the wall, the bass becomes really loud. Okay, so there is a pressure buildup. The membrane, the eardrum is actually a pressure sensitive thing rather than velocity sensitive thing. Okay, and then the velocity actually has a node. Node means that it's the minimum value at the wall. Okay, so that's what we're looking at. So as you see at the boundary, we have zero velocity. You can't move the wall, and all the energy is in the pressure. So what you have is always this kind of energy relation between pressure and velocity. Okay, kind of inverse relation there. Pressure builds up, it's actually double to the other nodes as well against the wall, and bounces back. So at the wall, the velocity reflects with inverted phase and pressure reflects in phase. Okay, so the way to kind of remember this, hopefully, is to also think about a bit of instrument acoustics. So I'll just sketch this up briefly. What happens if I have a one-dimensional object fixed at both ends? And what happens if I have it fixed at a single end? Okay, so if I have one-dimensional object fixed at both ends, then the basic fundamental oscillation pattern is this, okay, which relates, so the wavelength of this oscillation is double the length of this object, because this would make a full wave, okay? Now, if I have an object which is fixed at one end, then the basic oscillation pattern is this, evidently, right? And then the length of the object relates to the quarter of the length of the fundamental wave frequency, because that would be the full cycle. Okay, so actually I didn't bring the tube, any tubes here. Tubes. I don't see a tube. So what if you have a tube at home, you can even take the like a vacuum cleaner pipe, right? And if you do this, you get one frequency. If you do this, you get another frequency, right? Because if you do this, what you're actually doing is you're making a both and reflective thing. And if you do this, it's at one end, so you get an octave below. Okay, so actually from this, the other thing that's interesting, I won't draw the equation now. I also don't know it from the top of my head. But what you have here is that the harmonics are 1F, which is the fundamental, and then only odd harmonics, 3F, 5F. And here you actually get all the harmonics, 1F, 2F, 3F, 4F, and so on. Okay? So there's this other characteristic of the basic most one-dimensional physical body in relation to how it is fixed. And then from here, what you can remember is that if the end is loose, right, then what happens is if I have a wave coming through, right, so one state, second state, third state, fourth state, it is actually reflected back like this. Okay, whereas if it's fixed, one state, second state, third state, third up, it actually comes back with the inverse phase. Okay, so what I'm doing here is I'm drawing traveling waves versus standing waves. Yes?
Is the reflected one, the bottom like, sketch, the reflected like wave in the same path as the one that is
Yeah, it's the same
so
phase.
there's no delay in the reflection.
No delay there. Okay, so what I'm actually drawing here is something which is crucial, and that is the distinction between traveling waves right? This is a traveling wave, and a standing wave, which is more like this, and then back again. So you kind of have the peak and the trough stand in the middle. It could be elsewhere if it's a higher mode, it could be here and here. But in a sense, the peak and trough don't move longitudinally, don't move left and right in this sketch, whereas for a traveling wave, they do. And then the point is that the traveling wave actually becomes the standing wave due to superposition. So somehow or other, the reflected wave is back in phase with the forthcoming wave, and then they make a larger peak. Okay, so there's a bit of fun to be had here in terms of wrapping your head around it, but those are the main principle here. Okay, and then there are some really lovely. Oh, can I even do that? No, I can't even copy it. Let's do it manually then. There's some really lovely graphics available because, you know, the physics teachers, they can be really motivated, and if they know a bit of programming, they make these lovely things. So if this is still alive, it might be a lovely thing to have a look at. Okay, so here's a little standing wave demo. Okay, so reflection from fixed end from a free end. Let's do a fixed end. Slow motion start. Let's see how this works. Here it goes. Will take forever, and this is even fast. Okay, I think I can increase the time. Incidenting wave, reflected wave. So we're gonna look at both. So this is supposed to show you how a traveling wave actually can reinforce itself. Okay, there is the reflection. Oops, there we go. Okay, so you suddenly see how it's actually coming in phase with the reflected self. So the black dots are the resultant wave, and the red one is still the forward traveling wave, and the blue one is the reflected one. So you see that actually the two are coming in phase, and they make up the standing wave. Okay. Cool. And then this other one, are we there yet? Not there yet. Actually, where were we here? Kind of jump to another one anyway. So this is refraction one. Maybe I'm doing this at random a bit. Okay. So here the interesting thing is, doesn't come through. Restart, next step, pause. You know, there's the medium 2 index of refraction. Maybe it just didn't. So you're supposed to see what happens in the medium 2 if you have a different index of refraction, but it's not really happening. That should do it. Okay, here we go again. So this is the wavefront that is getting into the second medium. Okay, so you actually see how the angle is changing, because again, these are the, you know, the ways you can observe the waves, but actually the resultant wavefront is again a straight line. Okay, and you've seen that it is quite different. If I start with 0, okay, what do you expect to happen? What will happen? Yeah, it will be straight, but something will happen. What happens due to the fact that the medium is different?
It's like turn a little bit.
No, no, no. Well, the underlying thing, why does anything happen to start with? Because the medium is different, and therefore, what's different in a different medium? No. Well, that's the diffraction itself, this changing of the medium. Speed is different, exactly. So try to observe the speed here. And you see the reflected wavefront is much faster than the one coming through, right? So it slows down. But you see there is nothing funny going on with angles. Now, if I have a really sharp angle there, you see how actually things are quite funny. Lovely things. All right, seen that, done that. Cool. So let's get on with the show. Right. Yeah, no worries. So we had a reflection of the increased impedance boundary, and now we're going to look briefly at the fact that if you have a decrease in impedance, you get a reflection as well. Okay, so exiting solids, exiting tubes, right, getting into a medium which is more rare will also give you a reflection. Okay. Right, so we have at the exit, let's call it that, we have velocity antinode, so maximum velocity. The particles move more freely, we get a large velocity there, okay? And we have no pressure buildup, right? At the exit of the tube, there is no pressure buildup, okay? So all the sound is in kinetic energy, velocity component is doubled rather than the pressure component, okay? So it's an inverse of hitting the wall, exiting the tube is inverse, but both provide some degree of reflection. Now, the degree of reflection is actually very dependent on the abruptness of the impedance boundary. Okay, so if you look at the trumpet flare, right, it actually has the function of decreasing the reflection back into the tube. So it's giving you a gradual decrease in impedance, right? The thing is that by doing that, you actually make the standing wave a bit less stable, right? The resonance, to produce a resonant behavior, it's slightly more tricky. It's easier with the trumpet without the flare. But if you think about porting the loudspeakers, right? Typically there, you actually really want a flare because it will decrease the bandwidth of the peak, the spectral peak that is caused by this resonance of the box. Okay. In fact, I know some loudspeaker designers, and they spend hours talking about the shape of the flare in the port. Okay. And then I know some others who don't spend a second on it because they're like, no, you're never going to port your speaker anyway. Okay. What's the difference there? You remember I said something about this last year in transducers class? What's the advantage of a sealed box loudspeaker? Well, a ported box is just a full-on inaccuracy. Okay, a ported box will have a horrible time response. It will ring on like hell. It will make your bass sound louder, but much less precise. Okay, the funny thing about this is that we're so used to listening to ported boxes that if we hear a solid, tight bass coming from a proper sealed box, we're like, well, it's something, but it doesn't really do the thing, because we're really used to this imprecise, horrible time response of the port in your speakers. Okay. Typically, you can. The other thing that happens is that you have a sharper roll-off with a ported box. Okay, so technically you will get much less sub if you have a ported box. Okay, impedance decrease. Okay, so the way the things reflect is the other way around, as if you're gonna remember that. So this is the thing here. So you can also imagine it's kind of akin to the situation where one end is loose. So you see the pressure doesn't push against the wall and then comes back as a compression, but it kind of throws the ball out and then comes back, right? So there is, you can kind of intuitively see that there is a time behavior difference there. If it pushes against the wall, it kind of immediately jumps back, but if it throws the last ball out and that one comes back, it is actually slightly later, right? So that kind of intuitively, hopefully says something about how these reflections work. Okay, so standing waves, we talked about this already. Pressure component, velocity component, out of phase. And the fact that pressure builds up against the wall and velocity is zero against the wall. Okay, you've seen how this superposition, I kind of played it a bit early. Let's see the standing longitudinal waves. Maybe it's, these things look quite nice. Anyway. Okay, so here it is with both sides open. Form of the tube, vibrational mode, fundamental vibration mode. So this is what happens. Okay, so you see how the displacement, the velocity here is really minimal, and how the velocity here is actually maximal. Okay, so that's the displacement, right? It's a node, displacement node here, displacement antinode here, and this is the divergence from average pressure. Okay, so you see how the pressure here, the distance between these dots is quite stable, right? Whereas the distance, the density of the dots, the pressure here is changing the most. Okay, and then if I have one side open, this is what happens. Okay, so you see that again at the open side, the displacement or velocity is maximum. It moves the most, right? But the pressure, the density of the dots is fairly stable. So it's a pressure node. An open ending is a pressure node, velocity antinode, and then the fixed end here, you see, is the other way around. So the velocity is minimum. These particles can't move very much, but the pressure can build up right there against the wall. Okay, we can get a higher mode as well. Right. So this is what happens. So you get another antinode here in terms of pressure, an antinode here in terms of displacement. So typically, if someone says node and antinode, they refer to pressure. But if they really want to be accurate, then they name the type of node and antinode. That's a bit confusing because you see both are nodes and antinodes in that sense. First overtone, second overtone. Lovely dots going up and down, back and forth. And then both sides closed. Let's get the fundamental first. Okay, so now we have two velocity antinodes against the two walls. The particles can't move quite too much. They can move the most here. The pressure can build up against the edges and doesn't build up in the middle. Okay. Cool. Okay, so the exercise, well, it's kind of baying against explaining it, so we're probably gonna skip doing this. we've just done this. Maybe it's useful if you look back at the slideshow to kind of refresh your bits. Okay, relationship between wavelength and the tube. Well, we've just looked at this, so that's quite fresh. So here is the equation for a single open-ended system. If you want it, you might find it in the exam, you know, be able to play around with it, calculate any of these variables. Okay. And then we get into multiple dimensions. Okay. So we've looked at one-dimensional objects, fairly straightforward. In 2D, it already gets more complex. So what we suddenly get is a cyclic path around the object, in this case, an enclosed rectangle. Okay, so in a sense, what you get is that these reflections, again, are what we call specular reflections. Okay, specular reflection is your normal reflection, whereby the angle of incidence is the same as the angle of reflection. Okay, so what you have then is that you get a standing wave, because a wave that travels this direction reflects like this, reflects like this, reflects like this, and once it's back in the beginning point, it comes back in phase with itself and then creates the standing wave. Okay, so you remember the first little Java thing there when you saw that the forward traveling wave is actually a forward traveling wave, a backward traveling wave is still a backward traveling wave, but if you sum them up, then you actually visually see that it becomes a standing wave, that the peaks actually don't move left and right anymore. Cool. So diffraction in acoustics is what you can call bending around corners. Okay, so this is an interesting thing, because you will see that in the history of physics, they've actually spent quite some time puzzling over how on earth is it possible that a wave turns around the corner. But that is a problematic thing only if you consider it to be an error. However, if you consider it to be concentric circles, then it's fairly clear that after the edge here, the concentric circles have no obstacle to spread like that as well. So there's quite a few experiments around this. You can see these puddles of water that demonstrate this quite well. Okay, so there's quite a lot to say, well, not too much about this diffraction. What is interesting for us is that it is frequency dependent. Okay, so lower frequencies diffract more. And this has a relation to the fact that a small object or a low frequency is not an obstacle. Yeah?
Is it like on the same principle as the diffraction of light?
Yes. Yeah, it's very similar. It's a different scale of things. So what we get in acoustics, right, with objects like chairs and high frequencies, in the light experiments, you need, you know, really, really small slits and all the rest of that. And what you get, which is this thing which was puzzling for a while, is these interference patterns of light. Okay, so what happens if you have a very tight slit gap for the light to pass through, and you shine the light through it onto the wall? Well, you see the line, but actually around the line, you get little bits of diffraction patterns. Okay, so that was also quite puzzling in terms of, okay, how do photons do this, right? But then again, you know, is light a photon or is it just the behavior of the medium? Well, both of these are models and light is light. That's my solution. Okay, so it depends on the frequency. So what you can also think about in this sense is that if this is supposed to create a shadow, it actually needs to extend to multiple wavelengths, right? So for a low frequency, it will not create a shadow. But if it is taking longer, then it makes less of a shadow, or sorry, more of a shadow. Okay, and that's that. And then we have the slit diffraction. So slit experiments, fairly famous. So if you have an opening, then funny things happen. Again, the size of the opening in relation to the frequency of the wave does funny things. So let's look at these lovely patterns as well. Where are we here? Okay, and here you kind of see the slit experiment. So what I can do, I can increase, decrease the frequency. Okay. So if I increase wavelength, what happens to the frequency?
It's lower.
It's lower, yeah. So I'm lowering the frequency this way. So you see, if I have a fairly low frequency, it doesn't really do it. And then if I increase the frequency, I get more of this pattern. And then this is also dependent on the width of the slit.
Not the other way around. The wavelength is-
Well, it is the color, but in terms of the frequency, it's the same. So higher frequency is shorter wavelength. Huh? So actually here, you know, you have ultraviolet just beyond the visible spectrum. So ultra is above. So you know the violet is the highest frequency of light, and you have the infrared. So below red. So you know that the red is the lowest frequency of light. At least that's how I remember it. Okay. And then these are the frequencies in between. And then based on the width of the slit, you get things happening. And you can also modify, oh, you're actually just viewing the values here. Oops. So you get, okay, we've seen that. And then let's see the double slit experiment, which is even more famous. Okay, so I have two slits now, and then I get much stronger interference pattern right there. Okay, so spacing between the slits can actually provide quite some interest there. Okay, so that's the interference pattern, and this is the intensity profile. You can look at that as well. So what you have with the double slit is that the intensity actually goes much higher. See, these are lighter. In a single slit, they were actually tailing off much earlier. Good. And then diffraction around an object. Okay, so this is the intuitively simple thing. For low frequencies, you need a larger object for it to be an obstacle. Where is this obvious in psychoacoustics? That a small object is not an obstacle to a low frequency. In localization, how does this relate to localization principles? It relates to interaural level difference, ILD, right? So the point is that for a high frequency signal, my head is an obstacle. And therefore, if it comes from one side, in the other ear, the high frequencies will be much softer. If it is a bass coming from one side, the bass easily diffracts around my head. And therefore, in the other ear, it won't be significantly softer. So this means that in terms of localizing sounds, if it is a high frequency sound, we are more dependent on the level difference. And vice versa, if it is a low frequency sound, we are more dependent on the phase difference. Okay. So now if you go back to experimenting with panning algorithms, hopefully, you should know that panning the bass left and right with amplitude feels funny. And it does. You know that most people will actually put all the bass bang in the middle, right? And it's not just to do with the fact that, you know, you have a single subwoofer in most situations. It's also the sense of this being a natural thing happening. Okay. So in the room, if you have a bass band to left, it's funny. But if you have it on headphones, that's a total mind screw. Okay. So those are the things that these bits relate to. And then briefly about scattering, we will talk about diffusion, scattering. They're very akin principles. So what we're talking about then is non-specular reflections. So specular reflection, again, is the one which has the same angle of incidence and reflection. And if you have objects or obstacles or detail that is small in relation to the wavelength, then a lot of weird things happen. I mean, this is still only one blob, but if there was some more detail here, you would actually get waves dispersing in all possible directions. We will talk about this and quantify it at some stage later. Okay. And then resonance, we've seen this. Let's watch this last thing. Is a very prominent phenomenon for us. Resonance. Here is your mass spring system. Okay, that's your typical model of the simplest resonating system in physics. And you can play with the spring constant, with the mass, with the attenuation here. Let's start this going. Okay, so what we have here then is what we call a driven oscillator. Okay, so you have the exciter, the red dot, which moves sinusoidally. And then you have the spring, and to this spring is attached the blue dot or box, which has a resultant waveform, right? So what this shows is that something that is traditionally just a resonator, a mass on a spring, is actually a bandpass filter, right? So what we're looking at is that depending on the frequency of the resonator, here it's 2 radians per second. Hello, physics. Yeah. So if I increase this, let's go 2.5. Can I do that? And remember that this one is a bit funny and you have to pause it to change values, I believe. Let's try that again. We were looking at the amplitude diagram, right? So 2.5. Oh, come on. It doesn't let me change it. Resume. Slow motion reset. Maybe on a reset. There was something funny about this. There we go, 2.5. So I'm slowly increasing the frequency. And what I get, come on, start. Slow motion, oh yeah, it was too slow. Okay, so I'm slowly increasing the frequency. The other parameters are constant. And you see that the amplitude of the response is increasing. Okay, so if I manage to do that again, reset, so I'm going to go fairly close. So the omega based on these parameters is 3.16 radians. So I'm going to do a 3. So now I'm driving it with the frequency fairly close to its natural resonance frequency. And you see that the small amount of motion very close to the resonant frequency actually makes a whole lot of excursion. Okay, so actually every resonator behaves as a bandpass filter, right? So you see how, what is the first bandpass filter you've ever encountered in your life and fought against and struggled with? Huh? Well, no, but as a kid, you know, you don't really get what's happening in the ears. It's the swing in the park. You know, when you sit on the swing, anyone remembers their trauma at the time when they first sat on a swing and it just did not swing? And it took some time to figure out. Because what happens, right? You sit on a swing as a kid and you're like, you're doing this and it doesn't do anything, right? And then you try to do it even harder and it still doesn't do anything, right? So what did mommy tell? Well, probably mommy wasn't an acoustics engineer. So what's the point with the swing? Well, the point is to get to figure out the resonant frequency. So it's not about the force that you exert, right? You see here also the force that I'm exerting, the red dot is moving really quite a little. The fact is that the resonant system has its natural frequency, and if I come close, it's gonna really move quite a lot. So the point with the swing is, and hopefully some of you will go and try it later today, is, you know, you go to the park anyway for certain reasons. So if you do this, right, especially once you're stoned, you'll be like, okay, let's try it as well. So if you do this very slowly, right, it won't do a thing. If you do it very fast, we don't have enough room here, also won't do anything. What you really need to find is the resonant frequency of the swing, and then even the smallest exertion of force will get the swing in full motion. And how do you figure out what is the resonant frequency of the swing?
Just trying.
Yeah, but what? In trying, what is actually going on? How did you get to it? I mean, it's not like you were observing a kid and it's like, okay, the period duration is, right? You don't actually figure out the frequency. What is it that you figure out? What is it that you physically understand? When the swing stops. Exactly, yeah? So you're watching the peak, you're watching the excursion maximum, and you know, okay, when I'm at the maximum, when I feel it starts to pull me back, that's where I push my legs forward. And then you travel a bit forward and then you feel it. Okay, now I'm starting to travel back and you push your legs back, right? So what you're doing is you're really observing the system and making sure that you're acting in phase, right? So again, in phase, constructive interference. And if you know how to do this, you don't have to, you know, have a good timing as a musician either. You just have to figure out, okay, now I get the transition of the direction and I exert force at that moment. I exert force in phase with the system, and then the things start to work. Okay, elongation diagram. So here you see the exciter and you see the resultant waveform phase difference. Here we get into a bit more complex things. Okay, so what you have here is an interesting thing. So if I manage to do this again, so if you forget the amplitude response of the system, let's see, let's go really low frequency back again. Okay, so what I'm looking at then is that the phase relationship here, right, it's actually very close to the original. So when the original comes down, the whole thing comes down. When the driver goes up, the resultant goes up again. So it's kind of evident, you know, it's a fairly tight spring in this sense for the speed of motion. So it's kind of absorbing, it's kind of shaking a bit, but actually you slowly push it down, you slowly pull it up, it's not gonna do a significant phase difference like that. But if I overrun this, so if I take a frequency which is significantly higher than the, well, 5 should be plenty, yeah. Then what you get that the resultant is actually out of phase, exactly at pi, totally out of phase. So I'm actually pushing it faster than the resonant frequency, and I get this out of phase relationship. So if you look at the elongation diagram as well, you see that these are out of phase. And on the amplitude diagram, I'm actually past the resonant frequency. Okay. And then the other interesting thing here is that if I change the mass constant, let's say I double the mass, watch what happens to the frequency. Currently it's 3.16. Now it's 2.24. So it did go a bit lower, but actually for doubling the mass, it's just a very slight difference. Okay, so typically what you have is that the frequency of this resonant system is more dependent on the spring constant than the mass. And I believe if I have the attenuation to 0, now it's the time to have some fun. If I put attenuation at 0, I'm risking to blow up the system. Omega is 224. Let's double it back, double it up again. We said, let's do a 4 here. Start 1.58. So you see, I'm doubling the mass and the frequency is only slightly dropping. Which also makes sense because, you know, if you have a big guy and a small kid on a swing in the park, it's not that the small kid is swinging much faster, a little bit faster, but actually it's not even apparent to the eye. Everyone seems to be swinging at approximately the same speed. Okay, so we're almost there, pretty much there. Helmholtz. Okay, so in terms of the resonators, we've looked at the standing waves in 1 dimension, in 2 dimensions. We will slowly expand this to further dimensions as well. One of the interesting things is we actually did this last year. I took a wine bottle, which has a fairly cylindrical neck, which is important for this experiment. Did a through the bottle. Figured out, obviously it's a wine bottle, so 0.75 liters. That was fairly straightforward in terms of the volume. I took a little tape measure. I figured out the length of the neck. I figured out the surface area of the opening and did the calculation, and we were within 5 hertz. Okay, so this is actually a fairly solid bit of early acoustics. Helmholtz is one of the early pioneers here. This is his thing. This is what happens. So in a way, what you have is, and I will just, you know, try to open up a can of worms. Maybe someone is keen to get in and figure it all out. But the very interesting thing about acoustics is that there is a direct relationship to electronics. Okay, it's what we call electroacoustics. And there is also a direct relationship to mechanics. So the interesting thing is that what is acoustically a low-pass filter will have its counterpart in both physics and electronics. So it's a funny thing that you can actually translate between the 3 domains. And you can take really complex systems that will actually do this. Okay? So in this case, the volume is a bit of a low-pass filter, and the neck is a bit of a high-pass filter. And when you combine those two, you actually get a band-pass filter. Okay? So this is how you actually go from the physics, from the mechanical domain into the signal processing. And then obviously in the electronics, what is the low pass filter component? It's a coil. High pass filter component is a capacitor, right? So actually any arrangement of coils and capacitors can be translated into tubes. Okay? And can be translated into digital signal processing as well. and vice versa. Okay, so that's where these things become really interesting, and that's beyond me as well. But it's interesting to know how these basic principles actually hold in many different domains. Okay, so evidently it's not going to be exact. If you have flares on the neck rather than being cylindrical, it can be tough. You know, if it's a bottle that kind of has a widening neck, that's an issue as well. All the rest of that, consistent radius should be crucial as well. Okay, so that's it for today. For next week, check out the reflection of convex and concave surfaces. Okay, so beware, I'm not doing this just because, you know, I want to fill it up for you, but your ability to research things that you have not been presented will show in the exam, because part of the exam is exactly that. Maybe I should take the next lecture, we'll see, to actually introduce the exam in a bit more detail, the structure and all the rest, we'll see. Okay, so try to research convex, concave, spherical shapes. What do they do to sound? Okay, and think about the practical implications and look into acoustical lenses and the potential of audio frequency prism. That's an interesting one. So, you know, if you have a prism made of glass and you shine light through, it will actually spread out the frequencies. Have you heard of anything similar in audio? Kind of an acoustic screen, and I send sound through it, and here it's the bass, and here it's the mids, and there it's the highs? Me neither. Why not? Okay, it's a similar thing, it's just waves. So it could be possible, but maybe it's not. So see if you can dig that up. Okay. Then take your favorite wine bottle, whatever. Calculate if you like, not necessary. Maybe we should do it the next time. If we have 3 hours, why not? Bring in a bottle, get a little. By the way, one of the things that I'm surprised how many students, even at this level, make a mess of is how would you measure the frequency of the bottle, the resonant frequency? No, but measure, not calculate, measure. So I do, I record it, and then what?
One analyzer.
What analyzer? No. You see, that's the thing, because the spectral analyzer has a very limited resolution. So if you see a peak somewhere, it is typically a peak which is about 1/3 octave wide, maybe a bit less, but not much less. Okay, so there is no way of actually getting the exact tuning. I mean, it's just like when you tune your guitar, you don't look at the spectral analyzer, you look at the tuner. Okay, so the tuner is not a spectral analyzer. Make sure you don't commit this mistake if you're doing something similar in your final year project. I see it a surprising amount of times. I mean, evidently, you know, just to have a first guess is not an issue. But once you're there and you see, well, wait a minute, where is this peak? I can't really be precise because it's a different way of getting to the exact frequency. You can't do it with the spectral analysis, really. Okay, so you have a tuner, or the other way, if I don't have a tuner, what can I do? I think you did it in this in the first year, if it's still the same material. No. Now, if you look at the waveform, what can you do? Or did you do this in the second year, or maybe never at all? You can just select a certain amount of periods, look at the time duration, and then do the math. That's an option as well. Okay, so you look at the period duration. Okay, and then keep reading the books that I have there for you. Okay, and then we have these 3 main inaccuracies of FFT-based spectral analysis, which we will look at. So see if you can prepare yourself for that, and then we'll talk about that as well. Excellent. Thanks for coming, guys. Stop recording. I will upload